Same molecular formula, different structure. Are they isomers?
Yes.
Yep.
They're not.
Oh,
Not?
Because does this
Same
exist?
molecule.
Please pay attention. This is the most important thing about resonance. Does this exist?
Yes.
No, it doesn't.
Oh, well,
Does this
should have
exist?
started.
No, it doesn't. Resonance structures do not exist. What does exist is the both at the same time. That is called a resonance hybrid. Resonance structures do not exist because as soon as there are in this example there are 6 p orbitals aligned. As soon as that happens, they all merge and the electron density goes all over the place. So can this exist? The answer is no. Can this exist? No. What exists is the mixture of everything, the hybrid of all resonance structures possible for something. What is the hybrid? Hybrid is this and that. So how do we draw that? You probably have seen this structure being drawn for benzene often enough. The circle. The circle is telling us that the pi electrons are not localized. They are delocalized, spread over the entire ring. So resonance structures do not exist. They are drawn for our convenience. That's it. What actually exists is the hybrid. So I'll ask you again, are these isomers?
No.
No.
Because they don't exist. They're not. That is what exists. You guys with me? Everybody? Yes? So resonance is not a process. I sometimes, can I do this, guys?
No.
Yeah.
The answer is no.
Oh no.
So here are some symbolisms for us to notice. This arrow is specifically used, and you've used it in Gen Chem, haven't you?
Yep.
What have you used this arrow for?
Reversible
A
reaction.
process, a reversible process. A process where A becomes B and B becomes A. There's an actual dynamic process happening in the forward direction and the reverse direction. Isn't that what you studied in thermodynamics and kinetics? You can calculate the rate of forward reaction, you can calculate the rate of reverse reaction wherever they balance is where you have the equilibrium. But that's a process. Resonance is not a process. Resonance is not that this becomes that and then this becomes that again. No. They don't exist. So how do we denote resonance structures? Louder? Not really, because sometimes they're not equal. In this case they are, but sometimes they're not equal, and we'll get to that point also. That arrow is specifically used to say, well, these are resonance structures of each other, knowing fully well they don't exist. What exists is the hybrid. You guys with me? Everybody? Okay? Cool. Then let's explore resonance. Resonance, as I said the other day, is one of the most important topics in OChem, and therefore it's really important for us to understand resonance really well. Also, please make a note, resonance always leads to stability. If you can spread electron density, I equate electron density with joy. If I can spread the joy, it makes me happier. Go with that. If you can spread electron density, it will lead to stability, higher happiness. Okay, so what is the key requirement for resonance? There's only one. What? Louder?
It needs stability.
No, that's the consequence of resonance. Resonance causes stability. What's the requirement for resonance to happen?
Is it p orbitals?
And, yeah, go ahead.
Pi bonds?
No, p orbitals, what else? You were going to say something?
It was pi bonds.
Pi bonds equates p orbitals because you can't make pi bonds without p orbitals, right? The key is p orbitals, but then what should those p orbitals be? They have to be parallel. If they cannot be parallel to each other, you cannot have delocalization. And there was a hand up there also. What were you going to say?
I was gonna say unhybridized.
Unhybridized p orbital. But how many? Because if you have two, that's a pi bond. That's not delocalization. That's just a pi bond. You have to have more than two. More than two. 3 or orbitals greater than 2 that are adjacent to each other. Does everybody understand what adjacent means, right? More than 2, huh?
Can you just repeat what adjacent means?
Next to each other. Or next, basically, this atom has, and then the next one has, and the next one has, basically next to each other.
Would it be next attached or just next?
Doesn't have, well, okay, what do you mean by that part? Do you mean does it have to be a ring when you say attached? Because if they're not attached, how can they be adjacent? If I have one atom, I mean, is this atom adjacent to that atom? Can't.
It
But
can?
is
Yes.
that, are they adjacent? Is that what you meant, Mar? Or
Wait,
did you mean?
is that one?
Is this atom adjacent to that atom? If they're not connected to each other, how can they be adjacent?
Okay.
Is that what you're asking?
Yes. Mhm.
Or were you asking that do they have to be a ring?
Well, either way, I mean, that's what I'm trying to figure out.
Adjacent means atoms attached to each other. Okay, that's basically what it means. Atoms in a structure that are next to each other, attached to each other. They don't have to be carbons, by the way. All we need is unhybridized p orbitals that are parallel. So, what are the situations where you should expect resonance? You can expect resonance A when you have multiple bonds, meaning double or triple bonds, because they have pi electrons, pi bonds. So when there are multiple bonds alternating with single bonds. Those are the structures where you should expect resonance. For example, what's the hybridization state of each of these carbon atoms? Let's start from here. Hybridization. Uh-huh.
SP2,
Uh-huh.
SP2,
Uh-huh.
SP2.
Agreed? Does this have an unhybridized p orbital?
Yep.
How about that? How about
Yeah.
that? How
Yeah.
about that?
Yep.
That's adjacent p orbitals, and since it's acyclic, it can rotate and all, so yes, they will be parallel to each other. So who's to say where the pi bond is? Is it between these two p orbitals, or is it between these two p orbitals?
Between both sets,
Where is your pi bond?
all of them.
All of them. That's resonance. It's not here or there, it's here and there continuously. So, one example that I gave you of butadiene, once again, you have pi bonds, multiple bonds, double or triple, alternating with single bonds. Every carbon is sp2, in this case, okay, every atom is sp2 hybridized, which means every atom has an unhybridized p orbital that can be parallel. That's what I meant by adjacent. Got it? Yes? So, that's one situation where we should expect resonance. Should we expect resonance here?
No.
Not at all?
A little bit, not the whole thing.
Not the whole thing, fine. But we should expect resonance at least in this portion of the molecule. Right?
Yep.
Same thing. Are we all, yes?
I thought that it needed to be more than 2.
More than 2 p orbitals. So
Oh,
isn't that 4,
Yes.
right? More than 2 unhybridized p orbitals.
I was just looking at the pi bonds.
Yeah, so 1, 2, 3, 4. Yeah?
And over here?
How about this one? Can it have resonance? Yes, no, maybe. Where? Right there. Exactly. You have multiple bonds, because multiple bonds means pi bonds, which means p orbitals, and that are alternating with single bonds, yes, you can have resonance. Yes.
For the last two examples, how would that look in 3D space?
Say that one more time.
How would the last two examples look in
Which,
3D
these
space?
two?
Yeah, because
I mean,
the top of the pentagon one.
yeah, so that's not part of resonance. The delocalization, okay, I'm not good at drawing, but I'm definitely going to try. The p orbitals are on this carbon, this carbon, this carbon, and this carbon, right? Isn't that right? That doesn't have p orbitals because that's sp3 hybridized. So can these merge?
Yeah.
That's basically it. And we will draw resonance structures. First, let's understand where to expect it. Then we will practice drawing resonance structures and then drawing hybrids. So maybe that. So the only delocalization that exists is in this portion of the molecule, not that.
So the electrons can move freely in the bottom.
The whole, yeah, by the way, pi bonds, whenever we talk about pi bonds, it's not just overlap of that, it's overlap of both. It's one pi, p orbital, so it's overlapping top and bottom. So yeah,
So just the top part that wouldn't have any
we'll have
floating.
one merged channel, and then bottom there is also a merged channel. Where are the electrons? All over the place. So where are the electrons spending time? They're spending time over these 4 atoms, but not that, because that's not part of your resonance. Make sense, everybody? So right now what I'm trying to do for us is for us to list down when to expect resonance. What are the structural characteristics that will help us say, oh yeah, that can have resonance, or this cannot have resonance, so on and so forth. Once we're done with that part, we will then do examples. We will draw resonance structures, we will draw resonance hybrids and all of that stuff. Okay, can this have resonance, guys? Can this have resonance?
No.
No, it can't. Exactly. It has to be alternating with, the multiple bonds need to alternate with a single bond. There are 2 single bonds together. So this cannot do resonance. It's not, those are localized double bonds. They cannot spread around. These are localized. Those pi electrons are stuck here. These pi electrons are stuck here. They cannot be delocalized. Does that make sense, everybody? Yes? So that's one structural feature where you should expect resonance. The next structural feature is when you have, write it first, I'll explain. When we have allylic, and we'll talk about what that means in a second. Allylic lone pairs. Okay, so let's understand what allylic means. Then I'll draw a few examples to illustrate that thing, whatever. What does allylic mean? Allylic means one atom away from a double bond. When something is one atom away from a double bond, that something is said to be allylic. So just FYI, or rather as an example, if we have, let's say, I have a double bond, and then I have, right? Yes, should there be, by the way, should there be charges here? Where what? Right, do you guys agree? O should have a minus charge, absolutely, please. Calculating formal charges there are shortcuts to that which we talked about on Monday. Noticing that oxygen is making one bond and has 3 lone pairs, that means this has to be negative, has to be. But anyways, allylic lone pairs, meaning a lone pair of electrons that is one atom away from a double bond. So that these electrons are allylic lone pairs. Allylic, sorry. So allylic is something that is one atom away from a double bond. You guys okay with that?
Mm-hmm.
Yes? So whenever there are lone pairs of electrons, whether ionic or not is not the point here, but there are lone pairs of electrons that are one atom away from a double bond, there will be resonance. Each of these atoms will be sp2 hybridized, because remember, resonance leads to stability. So this is where VSEPR doesn't work for us. This is where VSEPR becomes that we can see some shortcomings in the VSEPR theory. And one of the shortcomings is that, hey, if you followed VSEPR, by the way, if you follow VSEPR, what should be the hybridization of the oxygen atom?
SP3.
But does sp3 atom have an unhybridized p orbital? Does sp3 have p orbital?
No.
No.
So can an sp3 hybridized atom do resonance?
No.
Guys, let's do this again.
Oh.
Please wake up. Does an sp3 hybridized atom have unhybridized p orbitals?
No.
So can an sp3 hybridized atom participate in resonance?
No.
Why? Because the minimum requirement you need for resonance is unhybridized p orbitals that are parallel to each other on adjacent atoms. So if an atom doesn't have p orbitals, can that atom be part of resonance?
No.
No.
That is where VSEPR falls short for us. Because let's put it aside for a minute. Let's just put it away. I don't care about VSEPR. What if? What's the hybridization state of this carbon atom? sp2, so it has that, right? What's the hybridization state of that carbon atom? So it has that.
Mm-hmm.
Now let's pretend VSEPR doesn't exist. Let's assume that is not sp3. Let's assume it is sp2. If it is sp2, what does it have?
It would have two lone pairs instead.
It still has 3 lone pairs.
Yeah.
But, exactly. One lone pair exists here.
Mm-hmm.
One lone pair exists here. Where is the third lone pair?
In the p orbital.
That works better for us because we know it's stable. VSEPR can't explain this to us. So VSEPR, we have to kind of move a little bit away from VSEPR and say, okay, what if it were sp2 hybridized atom? Now can we have resonance? And resonance is always more stable. If something can participate in resonance, it leads to stability and therefore it will do so. Does that make sense, everybody?
Yep.
So, having lone pair of electrons, one atom away from a double bond, also allows resonance to take place. We good?